Hello, I'm Peter, and I'm here with Maxime to present some of our work on delegated compositing. Delegated compositing encompasses a vast sway of different components of the rendering architecture. This talk is certainly not an introduction to any of these areas listed above, but since Lacrosse is still in active development, I would clarify that Lacrosse can be viewed as Linux Chrome running on a Chrome OS device. Simply put, Lacrosse is a Wayland client and Ash Chrome is our Wayland compositor. So one detail I did want to cover is some of the terminology around quads and buffers. The various layers of Chrome at some point produce rasterized texture buffers corresponding to different elements on the screen. For web context, this it comes from high up in the stack, like Blink. From where we sit, our focus being Wayland, all that we really need to pay attention to is what are the rasterized buffers and where are they located on the screen. All information related to the where is placed in quad structures, and a reference is made inside each of these structures to the corresponding buffers. So we only have two important rendering objects, quads and buffers. Given that, we can now move on to the question of this presentation. So what is delegated compositing? Lacrosse before delegated compositing looks like the image here. We have many quads that constitute the window of a Chrome browser instance. Originally, all of these quads were composited in the Lacrosse browser and were sent through Wayland as a single surface with a single buffer. With delegated compositing, instead of compositing these rasterized quads in Lacrosse, we simply send them over Wayland as subsurfaces and buffers. Our compositor, in this case Ash Chrome, then composites these buffers and quads at its discretion. It is in this way that we say the compositing has been delegated. So this diagram flowing from left to right, we see a portion of the rendering pipeline of Chrome. Normally this pipeline would proceed to the compositing stage. However, in its place, instead of compositing, we simply decompose the resulting aggregate frame in gray and send it over Wayland. The details of this decomposition are complex, but in summary, all of the quads of a frame are converted into the subsurface and buffers of Wayland. The entire frame of Lacrosse is sent over Wayland. It is then constructed back into a compositor frame on the Ash side, inside EXO. The point is that normally what would be composited into a single buffer just gets forwarded. So if delegation involves such deconstruction or reconstruction, the question is, why would we do it? Above, I have listed some of the advantages of delegation. So the double composition in the non-delegated case comes from, number one, the compositing on the Lacrosse side of the entire window, and then, number two, the compositing of that Lacrosse buffer in Ash onto the primary plane. With delegation, not only can we avoid this double composition, but we can also avoid the GPU memory buffer allocation associated with compositing on the Lacrosse side in the first place. So also, some of the quads don't even have buffer backings. They don't have any memory associated with them. And they're in fact only just solid colors. This is more common on the web than one might think. Delegation allows us to simply forward these color quads with minimal CPU overhead and zero GPU cost. So in some cases, delegation ends up as being a trade-off between GPU usage and CPU usage. To avoid any negative impact of delegation, we conditionally revert back to compositing in Lacrosse when the complexity of the frame exceeds a certain threshold. Over time, we have significantly reduced the synchronization overhead. So Maxime will share some of the deeper details on how this was done. So over to Maxime.
Thanks, Peter. So our delegated compositing work required some changes at the ozone Wayland level. That's the backend that Lacrosse uses to communicate with EXO, which is a Wayland compositor spinning on the Ash side. The first problem was the initial design of the buffer management. The buffer management is used to import Wayland buffers that are backed by DMA buffs created on the GPU process side and attached to attach these Wayland buffers to Wayland surfaces. These are the Wayland surfaces are actually the fundamental pieces of each window. And before the delegated compositing work, Chrome composited all the quads in a single image that was further scheduled as a primary plane. And that image was basically DMA buff that was back in Wayland buffer that allowed only one plane to be submitted, and we needed something else. On this diagram, you can basically see how non-delegated compositing works. So key output device allocates an image via libgbm, then pixels are written into the image, and after that, it schedules a primary plane, which is further passed from Lacrosse browser to EXA browser side, and then to Ash this process, and then that's overlaid. So the solution to this problem was to utilize Wayland subsurfaces. These are helper surfaces that can create a single window. They can also be stacked according to the Z order. This information is passed as a part of Wayland overlay config. We also created a so-called overlay processor delegated, which decided which quads can be promoted as overlays. In the beginning, not all quads could be promoted due to some limitations like rounded corners and subpixel positioning and others. And after these quads are promoted as overlays, overlay configs for these quads are passed to Wayland, and Wayland buffers that represent an image of each quad is attached to on Wayland subsurface. On this diagram, you can basically see the idea. The subsurfaces create a single window. So we have a root surface here that have all the subsurfaces attached to that, and we can see the entire window. Yeah, and it's also worth noting that some of the quads can be picked up as hardware overlays, and others are just composited on the Ash side. And here's the another diagram showing the big picture. Here we have the GPU vis process on the Glacro side with the overlay processor choosing which quads can be promoted as overlays. Then these overlays are scheduled and passed to GPM surfaces Wayland. That's the surfaces representation of a browser window on the GPU side. Then all this information passed via merge pipe to the browser Lacrosse process here and sent to EXA. EXA then creates a compositor frame using these resources, which is further passed to Ashwiz process and further to Ozone DRAM. Basically, Ashwiz composites using all these composites as single plane and then schedules buffer swap. Another problem was a background buffer problem. Due to a limitation of Aura, EXA couldn't put subsurfaces below the root Wayland surface, so below this surface. And yeah, this surface, as I said, has all the subsurfaces attached. So while that was late according to the Wayland protocol, we had to come up with a solution to still be able to attach a buffer to the root surface. Otherwise, the window was never activated and buffers were not basically attached on the Lacrosse side, and we didn't see anything on screen. To fix that, it was decided to use an empty background buffer that basically does nothing and was not involved in the and it is not involved in the decomposition on the Wayland compositor side. As Peter said, we had some other CPU overhead problems when delegated compositing was enabled. The first problem was fences that were created for each raster tile texture. In case of heavy load, there could be up to 64 fences created for each quad. Why 64 is just because uh, there is a trade-off between delegating all these quads are as overlays or compositing them on the lacrosse side. So 64 quads is the number that we currently use at the threshold. So we could have up to 64 fences created for each quad in a single frame, and that took a big fraction of CPU time and degraded performance as a result. On this flame graph, you can basically see that whenever an end access call happened, it occupied about 10%, like here, 10% of all calls. Another problem was that textures that were overlaid from lacrosse were not real overlays on the ash side. As a result, they didn't have the jail fence attached. Instead, they used sync tokens. And whenever these resources were released, EXO had to create a fence for each returned resource. And that basically was another problem why we took about 5% of all the calls on the EXO browser process. Yes, creating fences and attaching them to the resources. Next, I would like to talk about the differences between EXO and other Wayland compositors and why one cannot have delegated compositing enabled on all Wayland compositors. Please note that Linux can also use Ozone Wayland. It's not limited to Ozone X11. And it can also use, in theory, delegated compositing, but it's limited due to lack of some protocols. So to make delegated compositing work, we needed the following features: solid color buffers, rounded colors, overlay prioritization, and others. While working on that, we also saw some implementation differences that one compositor may not follow specs, which resulted in bugs of Ozone Wayland implementation in overall. Now let's talk about the Wayland protocols. One of the most important things that Wayland missed and still misses as only X implements that now is the ability of creating solid color buffers. That meant that solid color quads could not be properly delegated. In the beginning, we created a tiny image that was further cleared with a desired color. However, that meant extra performance overhead. A solution was to create a so-called surface augmenter protocol that would allow to request Wayland buffers of that color and attach them to subsurfaces if a solid color quad is in the list of overlay configs. Next was the rounded corners. Some of the quads when composited on the lacrosse side can have rounded corners filter mask. However, that information was lost when these quads were overlaid. As before, we extended the surface augmenter further and passed this information using that protocol. Now EXO uses this mask and reconstructs quads with rounded corners, filter mask applied. Here you can see an example of quads with rounded corners. This is the Omnibox that doesn't have rounded corners mask passed. Now you can see that it has the rounded corners. And the Omnibox window actually consists of two quads here with rounded corners applied on top and one on the bottom. Now Peter will talk about opaqueness and other problems we had to resolve.
So early in development, delegated compositing was actually more expensive on the GPU than non-delegated compositing. This was because none of the opaqueness information was propagating through Wayland. The good thing is that we didn't need to write our own protocol. The ZCR alpha protocol provides a blending mode, and all we had to do was simply send this across Wayland. So on the left in orange is the blending before this change, and on the right, noticeably less orange, is the amount of blending after. Notice some parts are completely blue, meaning that all of the rendering in that area was an opaque quad. Some other challenges. So DIPS, device independent pixels, is always coarser than actual pixels. So this means that we cannot simply express our quad locations, which are effectively in real display pixels, as integer GIPs. This diagram sort of shows some of the problems. This ended up meaning that we needed to create new protocol just to set the position of quads to support fractional dips. This was also absolutely required for anti-aliased quads, those being quads that do not fall on pixel boundaries. Damage in Wayland can be pretty tricky. Part of the reason is that there are at least two damage protocols. Surface damage protocol is fairly intuitive, but buffer damage is a bit more complex as shown above. There are bugs here due to the challenge of getting this both right for both protocols. The complexities here are buffer scale, transform, and UVs. We had a few bugs with damage artifacts. Ideally, all those issues have been resolved. So finally, an interesting result of the lacrosse ash split is that the version skew between these two binaries is possible. So however, our version compatibility is not bidirectional. So lacrosse is always expected to be newer and the same version, newer or the same version of ash. So a change that is only in lacrosse does not require any backwards compatibility functionality. But if a protocol change or an assumption change occurs, this requires conditional code version checking. So above you can see an example of such conditional checking in the lacrosse Wayland client. And furthermore, a fix in ash may actually take many versions of lacrosse to propagate through.
In the end of this presentation, we would like to also express our special thanks to all Wayland contributors who are contributing to Wayland implementation for the past years. Thanks for watching and have a nice day.